Up next, we have Paolo Lucente from KPN, who will talk about building traffic matrices for supporting peering decisions. Paolo? Thank you.
So, good afternoon. My name is Paolo Lucente, and among the other things, I'm a lead developer of the pmacct software. And this afternoon, I would like to speak to you about traffic matrices, and especially in the context of peering. Agenda for today, brief introduction, a couple of slides about pmacct, and then we will get into the details. First of all, why speaking about traffic matrices? Or rephrase it, I'm trying to waste your time today. My answer would be not. Of course, I'm here, so what else you want me to say? And I think traffic matrices are very useful to a number of network operator activities, and for example, capacity planning, traffic engineering, better understanding traffic patterns, and of course, peering. And this is where we will be focusing today. Still, traffic matrices are important to a number of activities, but they keep behind the scenes topic. Like I was browsing some archives, and all I could find is very few contributions, and most of them were formal contributions, and the others were saying about the goodies of traffic matrices, what you can do with traffic matrices, a lot of things. Very nice, but I would like to say with this contribution, like where you can, what are the challenges, and try to answer the questions that you see over here. So, with a very technical cut. So, back once again to square number one, building traffic matrices for peering decisions. What is needed? What is our shopping list? It's about BGP, telemetry data, so NetFlow, sFlow, or similars. A collector infrastructure, system, storage, and of course maintenance and post-processing scripts. While supporting some operators worldwide building traffic matrices, what I've recognized is that the first challenge is not a technical challenge, it's an organizational challenge. And yeah, the 800-pound gorilla project, because you can already see that the shopping list includes something very different things, and maybe in a larger organization they can span across departments. So you can already see multiple people involved, different backgrounds, maybe a project manager, and things like that. So, I mean, that's the first thing to take into account. It's from an organizational point of view, maybe you have to gather a few heads together, and that's never easy. Speaking about, so let's start from the tool. What is a good enabler to build a traffic matrix? I'd say pmacct, which is open source, free software. pmacct, very poor choice as a name. It's an IPv4, IPv6 accounting package. And with the next slide, it will become more apparent maybe why I think it's a good enabler for the task. But essentially in this slide you can see on one side a number of traffic collection methods, so lib pickup, NetFlow, sFlow, and things like that. On the other side you have common open source relational databases, but also memory tables. pmacct is sitting in the middle. It's not just writing to the backend what it gets from the network. Instead, it also offers some data reduction techniques like spatial and temporal aggregation, filtering and sampling or subsampling, and also tagging and lookups. One of those lookups is, of course, BGP. What happened last year in 2009 is that pmacct was just a regular NetFlow sFlow collector, introducing things like writing to database and regular collector. What happened is that it was introduced a BGP daemon within the software as a parallel thread to the collector. So now you get two parallel threads. One gets telemetry data, the other gets and handles the BGP sessions. Features of this BGP daemon are it behaves as a passive BGP daemon, passive BGP neighbor, sorry, and that's also a nice implication that we will see in the next slide. And the other thing is that it's a multi-rip BGP daemon implementation. So why is that? Because imagine you have a very big network, and imagine that you are peering with the same people in various parts of the world. So you want to capture localized BGP information. You don't want to work out any global best path or anything like that. You want to capture all the local information and look them up. So why introducing a BGP daemon in a NetFlow or sFlow collector? The idea, the vision, if you want, was that, telemetry protocols should report on the forwarding plane, so should help the accounting of data. But telemetry should not report on control plane information. They should not try to transfer over and over the same information, right? So that's what would happen if you embed a lot of BGP information, for example, in a NetFlow. Every microflow is attached by the same information. It's much more optimal that you get your collector peering, BGP peering with your routers, so that the control plane is there, and then afterwards it's just keep alive, right? So. Approaching our shopping list that we said before, we said that one of the things that we will need is getting BGP to the collector. So the advice would be to get the collector to BGP peer with all the PE devices facing peers, transit, and customers. No best path computation. That means that you have all the BGP tables. Scalability is preferred to memory usage. And during some experiments, full BGP feed is around 50 megs of memory. That means that if you want to let the collector peer with more than 75 BGP peers, so more than 75 routers, you should take into consideration compiling it 64-bit, because you will get beyond the 4 gig barrier. Just as a note here, there is some tier 2 and CDN scenarios that have been taken care of. And in these scenarios, there are 100 plus PE devices sending a full BGP table. And 200 to 300 gigs of traffic sampled not very highly, and occupation of the CPU was around 5–6% on a commodity Intel dual core. So, I think there is room to scale over here. The idea is that the collector should IBGP peer with all the PE devices, best configured as a root reflector client. And here it's the implication of that I was speaking about the passive BGP neighbor. A nice implication is that because you get always an open message from your routers, essentially you can see what is the remote AS, and you can always reply with that same remote AS to each of your routers. So that means that a single collector can IBGP peer across sub-AS boundaries or across AS boundaries if your routing domain is spanning across multiple ASs. The most important thing when building a traffic matrix in relation to BGP is that the next stop has to represent the so-called remote edge of the network, right? So you need to know where traffic is getting out of your network. This is a very typical scenario for many MPLS network, not all, but I mean a very classic scenario. But of course, there might be some corner cases or some cases that might require some more smart thinking in this sense, and which is hop by hop routing, BGP confederations, or maybe a large amount of routers with default gateway or partial routes. What happens is that in these cases, the BGP next stop that you see at the router where the flow is entering your network is not necessarily where it will exit your network. And so in that case, you can follow up. Remember that you have a multi-rib implementation, so you can jump from one rib to the other until you reach the remote edge of your network. And then switching to telemetry data, so NetFlow or sFlow, the smart thing is to export, once again, from all the PE routers facing peers, transit, and customers, but ingress-only measurements. I mean, why is that? Because traffic is routed to destination, so plenty of information where traffic is going to, and that's enough. But instead, it's crucial to understand where traffic is coming from, especially if you are interested into who is injecting traffic into your routing domain. And in this sense, if you do ingress measurement at the PEs, what you have is for sure, okay, the input interface. But if the protocol allows for that and the implementation of that protocol allows for that, you might also have the source MAC address, which is very handy for when you are peering at public exchanges. So when you have cases in which you have one interface and multiple neighbors off of it. And of course, NetFlow or sFlow can implementation can give some data reduction techniques available at the PE, for example, sampling, no problem with that. There is also sometimes available aggregation, and that is also fine. You can strip off things that are not required at the PE. But be sure that you carry IP prefixes, source and destination IP prefixes. And why is that? Because still you can, doing a lot of BGP, but still you can be lending part of your IP address space to customers or to other people. And in that case, of course, if you are aggregating and removing also the IP prefixes, then you don't know anymore, where traffic is coming from or going to, or very rough indication of that. About the telemetry export, I can see a few scenarios over here. First of all, let me be realistic. I mean, I'm myself a developer of a telemetry collector, and my personal opinion is that there is not a single collector that fits all the bill. And and I think that the toolbox, in this sense, can be extended to some tools, let's say Ang tools. And in this sense, I mean, what I can see is that, you can export the telemetry to all the Ang collectors from your routers. You can involve multicast. It's always elegant and niche and nice and smart. Or you can also resort to a dual tier sort of solution. So you can perform the export to some replicators, let's say 2 replicators, mastering in standby fashion with a heartbeat protocol running between them, and then they will fan out the data to the collectors. And in this sense, on one side there is things like flexible NetFlow, which is rapidly picking up, which is very nice to see. But this is not very wide deployed at the moment. So it's crucial that collectors can discriminate traffic, because what can happen is that traffic that you are sending is not for all the collectors. So very important that for collector developers. And to capture with the workflow the telemetry data BGP correlation, we have a workflow in 4 steps. Let's say that everything is done from the perspective of the orange ball, which is the observed routing domain. And step number 1 would be that all the PE routers send full BGP tables to the collector. And step number 2 would be that there is some traffic flowing through. And that triggers step number 3, which is sending telemetry data to the collector. Step number 4 is looking up this telemetry data into the collector to see if there is a corresponding BGP table where BGP data, control plane information can be looked up against. In the most simple scenario, in the most basic scenario, this is done just by comparing the source IP address of the, for example, NetFlow agent and the source IP address of the BGP peer. Of course, all sorts of mapping is possible in this sense. Getting to the storing part of data, it is wise to employ aggregation, right? And aggregate both spatially and in the temporal dimension before writing things down. So what I'm saying is it's not always the optimal solution if you are not doing security or forensics, for example. It's not wise to log to the disk every microflow or every sample that you receive from the network. And so, by aggregating, you make an optimal usage of system resources, and when you are building reports, you are avoiding expensive consolidation of micro-information, essentially. And this is very suitable for project-driven datasets. What I mean by this is that, you build datasets which are good for a project, for a task, or for a small set of tasks. And then, of course, if you have something different, like you have to do billing still with NetFlow or sFlow and things like that, then you build a different dataset, maybe also with a different tool. And that way, yes, you waste a little bit more space because you're building several datasets, but then you have a very, tied up sort of system for all your needs. Open source relational databases appear a natural choice for the task, right? They are able to handle very large data sets by themselves. They have a flexible and standardized query language, so no need for a developer of a collector to reinvent the wheel. And one very important point is that, they offer solid and evolving storage and indexing engines. So once again, there is no need to invent the wheel once again. And that also adds to the scalability, because essentially if you use a relational database, you can always employ clustering or partitioning, once again, both in spatial and temporal dimensions. Just to touch a little bit ground, this is a bit of an SQL schema. Don't take it too seriously. Don't have an heart attack because of SQL at Nanook. But this is just to give you an idea, right? This is how your data would look like once on the disk. Like a tag, because it's always nice to tag things, BGP primitives, counters, and a time reference. And of course, this is an example only because you can always freely mix and match BGP primitives with the layer 1 to layer 7 primitives. Post-processing, a few examples, like just to let you see how simple it is to retrieve data out of a relational database and what you can do with it. For example, you can see very easily traffic delivered to a peer per location, because you are peering with the same people in multiple locations, so maybe you want to see per location, maybe not. All opportunities are available. And then there is a nice example, aggregate AES paths to the second hop. Imagine that you are a CDN or you are a tier 2 provider and you are buying IP transit from somebody. And of course, the first thing you want to do is that, your IP transit provider is never a friend. It carves money out of your pocket. They are bad guys. So, so essentially, what you try to do is, to aggregate AES path to the second hop. So you try to see right the common denominator right after your IP transit provider, who you can peer with and get most of your destination of the traffic, instead of trying with, peering with everybody, which maybe it's not always an option. And then it's also very easy to focus on peak hour data. For example, you want to see for the last month every time what happens at 8 p.m., right? You can do that very easily. You can do every sort of top-end statistics. For example, here there is an example of grouping BGP peers of the same kind, for example, using local preference to do that, or retrieve a traffic matrix or a subset of it, purpose being maybe you want to inject data into a third-party tool. It's nice to play with the traffic matrices, like in the last, I show you in the last couple of slides. But it's always nice to be able to inject data into third-party applications. So if you can integrate the tool that does that produces you the traffic matrix, so if you can do that with third-party tools, you can have some very interesting things. For example, you can integrate a traffic matrix into traffic planning and traffic engineering application, like the Cariden one. And what happens is that besides playing with the traffic matrix, you can also play with the what-if scenarios, which is also very interesting. What Cariden says about integration of a NetFlow or sFlow-based traffic matrix with traffic planning application is very interesting. What they say is that essentially, interface statistics are always the gold standard, and that's because it's what you base everything in your network, like traffic engineering, but also policies and things like that. On the other side, I mean, NetFlow or sFlow, they are very commonly sampled, and so they will never have they will never be very precise. There will be always an error. So what happens is that you can use interface statistics as a scaling factor, as a fancy scaling factor for your NetFlow or sFlow traffic matrix information. This is a very interesting topic, but I felt to put a pointer to a previous NANOC presentation about this, because you can spend another half an hour just delving into the topic. So essentially, interface counters are the most reliable source of information, and that means that you can collect NetFlow or sFlow as convenient. So it means that you can do a sort of best effort, try best effort to cover your network with the traffic matrix. So you can just have a subset of the POPs or subset of the routers covered, or use some more sparse sampling. That's because you have still your interface counters. And then use a regression method, like the one that we said before, like the Cariden demand deduction or similar. I mean, there are also other applications out there doing the same. Last topic for today, scalability, because it's true that you can scale it up very well, because you don't do very fancy thing within the collector, but still at some stage you will hit a barrier that can be memory, so you can't store all BGP full routing tables into a single box or CPU because you have because you have a lot of telemetry data. So divide et impera approach is very valid. So you can assign PE, still coupling telemetry and BGP, never have to decouple them. So you can assign PEs to collectors, and in turn you can assign collectors to databases, or you can cluster the database itself. Tricky scenario in this sense is when there are BGP next hop follow-ups, because of course imagine that you are splitting things among multiple boxes, then it can end up that you want to follow up the next hop and the BGP rib of that neighbor is on another box. So you can either have all gateways or root reflectors peer with all collectors, or put all the eggs in one basket, or do some BGP peer mapping, because that is also some valid approach. Intuitively, the matrix can become quite big, and of course, some data reduction techniques can be used at this, for this purpose. So you can keep smaller routers out of the equation, or specific POPs out of the equation because they are negligible to the traffic matrix. Essentially, the whole purpose of the thing is stripping out negligible entities to reduce dispersion while still keeping a very good overall picture. So you can also filter out a specific class of customers. Maybe you have a very collapsed network, so you are already running everything out of very big boxes, and but for example, you can still strip out serial customer or things like that. And then you can also strip down things which are not essential to your specific scenario. For example, you are a CDN, you are very interested in upstream traffic, but not very interested into downstream. And the vice versa is true for an ISP. You want to know where traffic is coming from, and not really very interested in where you are sending traffic to, maybe. Of course, you can also do some more sparse sampling, or put thresholds on traffic relevance. And then let's not forget project-driven dataset, because somebody can say, hey, but if I use this approach, so a traffic matrix for billing, security, whatever, well, you are saying that it won't scale at some stage. Yeah, that is a wrong sort of consideration, because if you are trying to do something different, maybe you would aggregate data differently. You would not use a traffic matrix in the first place. And to conclude, my penultimate slide, it's just to give some further, some pointers, because essentially, because of time constraints, we can't approach all the topics. So there are so many topics yet to be approached, like, AS path radius, communities filter, asymmetric routing, that is very important one, but also entities on the provider IP address space. So you can look up previous presentation done at UK 14, and of course you have also other pointers for examples or implementation notes. Thanks very much for your attention. Any questions? Good.
Okay. Thank you so much.
Thanks.